Welcome back to another session on Fourier series. In this particular Fourier series, before we get into computing the A's and the B's in the trigonometric Fourier series representation, I want to just point out a couple of reference items. In particular, if you're computing the A's and the B's, you may need to familiarize yourself or remind yourself of some trigonometric relationships, and those can be found in Appendix F and G of the textbook. Also, in the back cover, inside the back cover of the textbook, are some Fourier series representations for four particular waveforms, and we'll look at those quickly from the textbook. But those are a square wave, a triangular wave, a half wave rectified sine, and a full wave rectified sine. The A's and the B's are already computed for you for those particular representations, and I want to make you aware that those do exist, and they're in the inside back cover of the textbook. We'll then go into finding the formulas or showing how those formulas arise for the A's and the B's, and then we'll see about computing some A's and B's for a particular periodic waveform, that being a pulse train, a periodic pulse train. As a reminder, we have the trigonometric Fourier series that we're dealing with in this class. We have the average value of that waveform, a sub v, and so if there is no average value, that will be 0. And then we're looking at the A's and the B's that are coefficients in front of the different harmonic components of the cosine and sine terms. But before we get into computing the A's and the B's, as I said, let's just remind ourselves of what we can do. In computing the A's and the B's, we're actually going to be looking at integrals of sinusoids. It might be the integral of a product of a sine and a cosine, or a sine and a sine, and the frequencies or the arguments on those sine and cosines most of the time will not be the same. And one way to do that then is to expand that product into the sum and difference of cosines and sines. Here I just give one example of the sine alpha sine beta product. And then it's easier to integrate the cosine of alpha minus beta, and essentially that's what you're seeing here in this integral of sinusoids where we're multiplying sine and cosine. Effectively, you find that product or rewrite that product as a difference of the sum and difference of the angles or the arguments, and then go ahead and integrate those expressions. And those formulas are actually found in Appendix F and G of the textbook. If you go to your textbook and in Appendix F, you will find in items 7, 8, and 9 these relationships for the product of sine and sine, cosine and cosine, and sine and cosine. Those are pretty helpful in evaluating these different integrals, where the integrals are actually found in Appendix G. And you might be interested when you actually have the product of a sine and a sine with different arguments, cosines with different arguments, or a sine and cosine with different arguments. And a lot of times we do want to remember what happens when we integrate a sine squared or a cosine squared, and we'll be specializing these integrals to be existing over a fundamental period, where the fundamental period is related to the fundamental frequency, and consequently all the harmonic content will be integrated over that fundamental period, and because of that we will have an integer number of sines and cosines in that fundamental period, and that's going to be critical when we're integrating. We'll find that a lot of those integrals integrate to 0. Just to get you maybe a more intuitive feel for what's going on. If we simply looked at the product of sine, in this case, I've sketched sine of omega naught t times itself, so that's sine squared. Now notice what's actually happening. We've now bumped everything up above 0, and you can see that we now have this average value. If we were to actually look at the area underneath that sine squared curve, we could see that the integral is going to give us this 1/2 expression based on the amplitudes. If we looked at the product of two different sines that have different harmonic content, and I believe here I'm looking at sine omega t times sine of 2 omega naught t, hopefully it's clear that this positive area would be canceled by this negative area in this interval of 1 second, which is actually the omega naught in this case, or the period. T is 1 second in the fundamental, and for that reason then the omega naught is 2 pi over cap t, or it's now 2 pi. But in this 1 second interval, which is the fundamental period, hopefully it's clear that when we have this harmonic relationship between the arguments of the product of two sines, and this generalizes. If I had sine omega naught t times sine of 3 omega naught t, we would have a similar picture in terms of the areas. Positive areas and the negative areas would cancel. And you're going to see that that's true in these remaining pictures. Here's another picture that illustrates the sine of 2 pi t times the cosine of 2 times 2 pi t. And again, we can hopefully see that the negative area is going to be canceled by the positive area. And we also have this positive area. That's the negative area of this positive area. Whoops, wanted to change colors. And likewise, we have this positive area being canceled by this negative area. So you can see that when we're multiplying these sinusoids together, if their arguments differ by some integer amount, it is going to yield 0 area underneath that integral. Again, here's a cosine omega naught t times a cosine of 2 omega naught t picture, and we have this positive area being canceled by the negative area, meaning here's this little half is that piece, and this little half gets the piece closer to 1, but hopefully you can see that those areas now cancel each other out. And that will be important in computing these A's and B's for specific periodic waveforms. One other piece of reference material I want you to be sure you're familiar with is the inside back cover of your textbook, which includes some Fourier series expressions, and in particular the square wave, which we've already looked at combining. We built this square wave up by combining sines in a particular pattern, and the pattern that we used, we didn't worry so much about the scaling factor, but we were doing 1 over n times sine of n omega naught t. If somebody gives us a square wave, all we need to do then is find the period, cap t. That can now be used to generate the omega naught. The other remaining parameter that we would need is a, and once we have a, now we can build this periodic waveform out of its combination of sines and cosines. In particular, for this square wave, the way that it's centered relative to t equals 0, it's an odd function of time. It's only going to consist of sines, and in particular, just the odd harmonics of that sine waveform. There's 4 such expressions in the back of the book. The other one is the half-wave rectified sine, and I don't have all of it here on the page until I scroll up a little bit more. But again, once somebody can identify the period of that waveform, which is a half-wave rectified sine wave, and once they know the amplitude, now they can generate the different harmonic content. We have the average value, a over pi, then we have one sine term at the fundamental, and the remaining terms are all cosine terms, and they are only true for the even harmonics, 2, 4, 6, etc. But once you have the period, you can now use that period t to find omega naught, and once you have omega naught, now you can build up this periodic waveform, and that's going to be important in one of the homework problems. One of the homework problems is a generalization of this, where you might actually have 2 half-wave rectified sine waves that are added together, and so you have an amplitude of one and an amplitude of a different value for the other. But hopefully you can now use this formulation to maybe more easily compute those Fourier series coefficients. So let's now look into determining the A's and the B's. Well, did I show you the inside back cover? Let me just go ahead and go there. If we go hopefully I can find the page number. That's 797, I believe. But here are the inside back cover. Here are the 4 different waveforms. We've talked about the square wave and the half wave rectified sine, and below those in the appropriate location are the formulas. What you'll need to just realize is that there is a typo here. This should be an equal sign and not a subtraction sign for little f of t that I've now highlighted, and hopefully I haven't messed that up completely, but you should be able to find that that full wave rectified sine wave is f of t equals 2a over pi minus 4a over pi, etc. So let's now look at finding the A's and the B's. First, let's find the formulas for those A's and B's, and that's now what I'm going to call how do we determine the A's and the B's. Suppose we wanted to find let's just look at finding the average value, the A sub v. And again, remember this formula that we have, this expression for the trigonometric Fourier series. Let's now find A sub v. And to do that, let's just suppose that we integrate both sides of the expression. And we'll integrate over one period. So suppose we integrate both sides of the Fourier series definition, which I just scrolled past. And we integrate over one period of time. Doing that, we now have, in terms of the left-hand side, we have this integral of x of t dt over 1 period t, and that's going to equal now this integral over the same period a sub v dt plus, and I'm going to now expand out my summation. I have a sub 1 cosine of omega naught t dt over 1 period. And now all of these are on the right-hand side. I'm running out of space, but I'll just say this is now a sub 2 cosine of 2 omega naught t. A sub 2 corresponds to the second harmonic of the cosine piece, and I could just keep doing that with the different cosines. And I also have all of these sine terms. The first harmonic then is 1 times omega naught t dt. B sub 2 is now sine of 2 omega naught t dt, and that just keeps going and going. But what you can observe here is the following, and this is what I was referring to when I was talking about the trigonometric relationships. Notice what happens if I now have any of these a's or b's. Let's just look at one of the a's and call it a sub n, which is the nth harmonic of the cosine, and it's now over 1 period. Meaning if we looked at that, we now would have something like this. And suppose that this was now our 1 period. Did I get an integer multiple of periods? Now we have 3 periods, so that little n would be 3 in this case. Now we have this positive area, and if I had sketched this properly, you would see, hopefully, that the positive areas cancel the negative areas for all of these terms other than this very first term and this left-hand side. All of the other terms integrate to 0 because the sum of the area under the curve is going to give us 0. And all of those terms then become 0, and that's true for the cosine pieces and the sine pieces, which says that we're then left with the left-hand side, which is this integral of the periodic waveform x of t over the fundamental period of time capital T, and that's now equal to this integral of a sub v dt, which is just, in terms of 1 period, a sub vt, and that now tells us then that a sub v is what we thought it was. That's just the average value of this periodic waveform over 1 period, meaning we integrate x over 1 period and we divide that period out, and a sub v then is our average value of x of t. What about if we wanted to find some other a's and b's? What if we wanted a sub 1? So now if we look for a sub 1, let's do the same strategy. In the first strategy, to find a sub v, we just integrated over 1 period. Now, a sub 1 is originally associated with the first harmonic. It's multiplied by, it's the coefficient multiplying or scaling the cosine of 1 omega naught t. Why don't we multiply all of our terms by that cosine omega naught t? Let's then multiply the definition of our Fourier series by the cosine of omega naught t. This is now the cosine term associated with the a sub 1 coefficient. And now, after we've multiplied the definition by cosine omega naught t, let's integrate again over the 1 fundamental period. That now allows us to see that on the left-hand side, we have x of t. We're going to multiply it by cosine omega naught t, and we're going to integrate it over one period. Then on the right-hand side, we have an infinite number of terms. We first have a sub v cosine omega naught t dt over one period, and hopefully you can see, well, that's just the cosine integrated over one period. That's going to vanish. Then we have plus the integral of a sub 1 cosine omega naught t times itself, so that's really cosine squared omega naught t, plus the integral of a sub 2 cosine omega naught t times cosine of 2 omega naught t dt. And we can keep going with all of those cosine terms, and we also have all of our sine terms. We have b1 sine omega naught t times cosine of omega naught t dt, and that's over one period t, etc., etc. And hopefully now it's becoming clear what's happening. We now have a lot of terms that have products of sines and cosines. And at the beginning of this lecture, I hinted at we needed to understand why those actually vanish. If we looked, for example, at the following, suppose we looked at a generic a sub n cosine of n omega naught t times cosine of omega naught t dt. We could rewrite that product of cosines using the trigonometric relationship for the product, and we end up with then this 1/2 factor. We have a sub n over 2 integral of cosine of the difference of those arguments, which is n minus 1 omega naught t dt over one period, plus a sub n over 2 integral over one period cosine of the sum of those arguments, n plus 1 omega naught t dt. And hopefully it's clear when n is not equal to 1 that now we're integrating a integer multiple of cosines over one period, and that integral now is going to vanish, as is this one. This again is some integer multiple of cycles of the cosine over the fundamental period capital T, and those are going to vanish. We also have the same relationship for the sine terms. If we looked at a generic sine term, let's say b sub n sine of m omega naught t cosine omega naught t dt over one period. That's what's on the right-hand side of that earlier expression. Again, we can take the trigonometric relationship of the sine cosine product, and that's going to give us this 1/2 of sine of m minus 1 omega naught t dt over one period capital T, and then we have plus b sub m over 2 integral over t sine of m plus 1 omega naught t dt. Again, we're going to have an integral number of sines in that one fundamental period if m is not equal to 1. And in both the m minus 1 and the m plus 1 case, those are going to go to 0. With all of those vanishing, the only thing that's left, again, the a sub v times cosine is going to vanish. This now leads us to the following. The left-hand side we still have. That was x of t times the cosine of omega naught t dt over 1 period capital T. What was on the right-hand side that we haven't looked at was the integral associated with the product of cosine omega naught t with itself, or we now have cosine, or this was the case when n is equal to 1, for example, and we can rewrite cosine squared as 1/2 plus 1/2 cosine of 2 omega naught, or we now have 1/2 dt plus a1 over 2 integral of cosine of 2 omega naught t dt, again over 1 period. And this second piece, because it's now 2 cycles in a 1 period interval, that goes away, and all we're left with then is this. On the right-hand side, we have a1t over 2 when we perform the integration, and that now leads us to, if we solve for a sub 1 is now 2 over t, this integral of the left-hand side, which was x of t cosine of 1 omega naught t. I'm emphasizing that we're looking for the a sub 1 coefficient, all integrated over 1 period. All of that then goes together to give us these relationships or formulas for computing the a's and the b's. Or in general, if we want the a sub n term, we just take 2 over the fundamental period and integrate over the fundamental period x of t times the cosine of n omega naught t dt. Likewise, for the b's, we have 2 over t integral with respect to, or over 1 interval, fundamental period cap t, x of t sine of m omega naught t dt. And those are now our equations or formulas for computing the a's and the b's in this trigonometric Fourier series expression. Let's now compute the Fourier series for a particular periodic waveform. So now let's look at the calculation of the Fourier series. The example that I'm going to use is going to be a pulse train, and let's say that that pulse now is half a fundamental period in width, but it's even. It's an even function of time t, and now at t it repeats, meaning right here this is going to be halfway between. That's t over 2, but then it starts again here at 3/4 t and goes up to 1/4 t beyond t. So this is now 5t over 4, and this is now 3t over 4. And over here we have minus t over 2. This is now a periodic waveform that's going on and on for all time. That's our periodic waveform, and let's give it an amplitude of a. We want to now compute the coefficients a sub v, a sub 1, a sub 2, or expressions for, and expressions for the b's. Let's now determine those coefficients. And before you even start determining these, you're going to start to see some patterns arising as you get a little bit more comfortable with these Fourier series calculations. One is, I hope you can see that we do have a non-zero average value since we have no negative value for x of t, it's all non-negative, and so we should have a non-zero average value. Also, x of t is even, and that's going to play a role in actually forcing the b coefficients to all be zero. But I'm maybe getting ahead of ourselves. Let's now find the average value. That's simply 1 over the period, integral over 1 period, x of t dt. And I didn't explicitly define what the period was, so we'll keep that a variable quantity, but we are integrating from only the interval of time where that function x of t is non-zero in 1 period, and that's from minus t over 4 to t over 4. It has an amplitude of a dt. So that now if we do the integration, we have a over t, t from minus t over 4 to t over 4. And substituting all of that in, hopefully we will end up with the t's canceling, and we have a over 2. That's now our average value, which is what we would have expected since the pulse width is on half the time and off half the time during our fundamental period. We've now found a sub v. What about a sub n? A sub n is now this integral, and we'll divide out the time t, and it's actually, we need to remember our formula has a 2 in the numerator, so it's 2 over t, integral over 1 period of x of t cosine of n omega naught t dt. And notice sometimes we can actually keep n as a variable and solve for the infinite number of a's with just one expression or one calculation. Let's see if we can do that here. Again, we can integrate this only when values when x is non-zero, and that's between minus t over 4 to t over 4. It has a value, a non-zero value of a. Then we have cosine of n omega naught t dt. And the integral of this cosine is a sine, and we need to divide out the argument relative to what's multiplying t and the argument of the cosine. We have 2a over t. We have the n omega naught that we've now divided out, and this is now sine of n omega naught t evaluated at these limits of t minus t over 4 to t over 4. Or this now becomes this 2a over t n omega naught sine of n omega naught at the upper limit is t over 4 minus the lower limit, which is sine of minus n omega naught t over 4. And sine of a minus x is minus sine x. That now actually allows us to combine those terms inside the square brackets. It really gives us 2 of the same amount. We now have a sub n is 4a over n t omega naught, and t and omega naught are actually related to each other, and we'll clean this up in just a little bit. Sine of n omega naught t over 4. Meaning, remember how omega naught and t are related. Omega naught is 2 pi f naught, which is 2 pi over capital T. Which now, whenever we see this product of omega naught t, that's just 2 pi. And that now allows us to rewrite our a sub n coefficients. Meaning, a sub n was this 4a over n t, but then it was times omega naught, which is 2 pi over t, and we had sine of n omega naught, which is 2 pi over t, times t over 4. And some of the 2's cancel. A sub n now becomes 2a over n pi, a being the amplitude of our pulse train, sine of, let me get rid of that 2 upstairs, n pi over 2. And you can see then that for some of those values of subscript n, or for some of the harmonics, if we have a particular integer multiple of pi, that's going to go away, and that's going to happen for these n even values of the harmonic little n. What about the b's? I already sort of told you what those are going to be, but if we now look at the formula, we have the b sub n's are 2 over t integral of t x of t sine of m omega naught t. What we're going to be playing with now is the fact that we're multiplying x of t, which is an even function of time, by a sine, which is an odd function of time. That product actually gives us an odd function of time, which is going to integrate to 0. Let's do just a few more steps. We now have 2 over t integral from minus t over 4 to t over 4 of a sine of m omega naught t dt. We can now integrate that, and again this is similar to what we've already done, except now we have to integrate the sine, which is minus a cosine, and we'll integrate or evaluate that at the lower and upper limits, and hopefully now you're starting to see what's going to happen. We now have minus 2a over mt omega naught, and we have cosine of m omega naught t over 4 minus cosine of m omega naught t over 4. And this is actually a minus inside that. I'm maybe getting ahead of myself, but this was a minus t over 4, but cosine is an even function of time. This now becomes what I had originally written down, cosine of m omega naught t over 4. That's now subtracting the same thing, so this now becomes 0, and now all of our b's are equal to 0. We now have created this expression for this pulse waveform. Our x of t expression is now our average value, which was a over 2, plus this sum from, and I'm not going to worry about the terms that are going to vanish. I'm just going to go ahead and build it all up. We have the coefficients, which are the a sub n's, and those are 2a over n pi sine of n pi over 2, and those are the a sub n's, which scale now all of the harmonics on the cosine. So this is now the cosine of n omega naught t that is weighted by this coefficient a sub n. And that's now the Fourier series representation of that pulse train written in terms of the trigonometric Fourier series expansion. And hopefully now we're in a position to possibly apply these periodic waveforms to linear systems, because we know how to analyze linear systems that are excited by sinusoids. And that's where we'll go later.